This is Algebra, section 11-3. We're studying how to multiply rational expressions. My name is Mr. Rupp, and in this video I will show you how to multiply rational expressions, how to simplify your problems before you multiply, and how to perform dimensional analysis. By the end of the video, you should be able to multiply rational expressions, perform unit conversions by dimensional analysis, and then using these techniques, how to solve real-world problems. Let's get to it. This is multiplying rational expressions, and the first thing we should do is get some terminology, vocabulary words out, and then just one in this case, one so far. So the first one we're going to look at here is rational expressions. And what exactly is a rational expression? Well, you remember what a rational number is, right? A rational number is any number that can be represented by a fraction, such as 1/2, 1/3. A rational expression, then, is an algebraic fraction. Basically, it's an algebraic expression where it has a numerator and denominator that are polynomials. Multiplying fractions, then. Again, a quick review then. If you had 1/2 times 1/3, that would equal 1 times 1. You multiply numerators straight across, and you multiply denominators. 2 times 3 straight across, and that gives you 1/6. If you had something even, like 2/3 times 3/4, okay, well, then again, same thing. Multiply numerators straight across, multiply denominators straight across. 2 times 3 is 6. 3 times 4 is 12. Now, this, along with this section here, will teach you how to take polynomial expressions like this and reduce them. You reduce this one, you can take a 6 out of both of these, right? Just to show you how to simplify, 6 divided by 6 is 1. 12 divided by 6 is 2. So this is the answer to this multiplication here. So let's do example number 1. All right, this is going to be on page 590. It says, find this product. All right, I'm not going to read this out to you. Well, we're going to do this with two methods, all right? So method 1. And you could kind of consider this the brute force method. You're going to multiply it all together, and then you're going to solve using the greatest common factor. All right? So let's multiply this all together. So what this ends up being is 5ab cubed times 16c cubed all over, 8c squared times 15a squared b. Well, 5 times 16 is what? 80. There's an a, and that's it. There's a b cubed, and that's it. And there's a c cubed, and that's it. All over. 8 times 15 is 120. There is an a squared. There is just a b. And there is a c squared. Okay? Now, what we're going to do is we're going to take the greatest common factor of 80 and 120. You know what that is? Well, without doing a whole bunch of prime factorization, okay, the greatest common factor between 80 and 120 is 40. So we're going to come down here and we're going to take 40 out of the top. Now we're going to do this in a couple of steps where the book does it just all at once. All right? But I'm going to do it in a couple of steps. We have 40. When you take a 40 out of 80, you're left with 2. Okay? And then a, b cubed, c cubed, all over 40. You can take 40 out of 120, you're left with 3. A squared, b, c squared. Now, we're going to leave this as it is. We have a 40 now, and we have the 2. Well, wait, we're not going to do that yet. What we're going to do now is we're going to look at the top and the bottom, and we're going to look at the A's and the B's and the C's and find out what's common. So over here, all right, for A, we have an A on top and an A squared on the bottom. So the commonality is just a single A, all right? So we take an A out of the top, and down here we had a 40, and so we took an A out of the bottom. And that left us with just an A. Up here, there was only an A, so when we took it out, that was it. Now how about B's? The B right here. There's a single B here and a B cubed up here, so when you take, there's at least a B on top and bottom. So we can take out a B on the top and bottom. When we take out a B on the top, what are we left with? We're left with B squared. When we take a B out on the bottom, that's all that's there. It just comes out. Now we're talking about C's. We have a C squared on the bottom and a C cubed on top. So there's at least a C squared in both places. So we can factor out a C squared top and bottom. When we factor out a C squared on top, we're left with C. Okay? When we factor out a C squared on the bottom, that's it. Now, don't forget the numeric coefficients, which I didn't write in here. These guys right here. All right, so there's a 2 up top, and we'll multiply those out here at the end. 2 and a 3 on the bottom. So overall, what this says is we can take out a 40 A, B, C squared times 2B squared C for the top guy, and a factor out of 40 A, B, C squared, and we're left with 3A. Now remember, the top and the bottom, you have to factor out the same thing, because 40ABC squared over 40ABC squared is 1. And if you multiply anything by 1, you haven't changed it. All right? So these guys cancel. And what you're left with is, in the end, 2B squared C over 3A. Think of this as a big giant puzzle, and you're having to figure out what that commonality is in the middle of the puzzle. For this next one, pause the video and try this one on your own, however you want to do it, and then start it up and we'll keep going. So I'm assuming that you paused it, tried it yourself, however you want to do it. We're going to try this method. This is going to be called simplifying. And this is method 2. So let's look at this guy. We'll write him out nice and big. 5C cubed times D over C4 times D. And that's all times F squared D cubed C all over 10C F to the 4th. So I'm going to use a different color to cancel these things. What can you cancel? Well, right off the bat, you look here, you have a D over a D. You can cancel those. That's 1. Here you have a C to the 3rd over a C to the 4th. Well, you can cancel a 3 out of both of these. And that leaves you with just 1. That's C to the 1. You come over here, you have an F squared and an F to the 4th here. So if you cancel the F squared, then that takes 2 of them away from here, and that leaves you F to the squared. And here you have a C and a C. You can cancel those. There's no D on the bottom left because you took the D out over here. So this D you can't do anything with, but you still have a 5 and a 10. Okay, so if you cancel the 5, that leaves just a 1, and you divide it into the 10, and that leaves you with a 2. So ultimately what you're left with is, well, here's a 1, the C's are gone, the D's are gone, the F's are gone. All you're left with is D to the 3rd power over, well, there's a C to the 1, okay, so there's a C, and this d is gone. There's a 2. The c is gone here, and there's an f to the 2. So I'll write the 2, and then there's a c, and then there's this f squared. And there you have it. Simplify before you divide. And a lot of these simplify right out. Let's move on. Okay, example 2 then says this is applying expressions involving polynomials. So you look at this, and what's the first thing you're going to have to do here? There's something that you could do right off the bat if you wanted to. All right, how about you can cross cancel this x with this x squared, okay, and what you're left with then is x minus 5 over 1. I'm going to leave it that way for a reason. And then you have a single x up here over x squared minus 2x minus 15. Well, so far so good, but that really hasn't gotten you very far. Well, what about down here? Well, let's just multiply the numerator across then. Okay, so we end up with x times x minus 5, which is why I left it up here. Okay, so multiply numerator straight, multiply denominators straight across. All right, we're left with x squared minus 2x minus 15. Okay, so the polynomial here, we have to do what to? We have to factor it. So coming down here then, we have x over x minus 5 over, so what multiplied together gives you negative 15, and added together gives you negative 2. Think about that for a second. You know these are obviously that. Okay, well, how about negative 5 and positive 3? Well, now we have this wonderful algebraic rational expression, and it's got a common term in the numerator and the denominator, which allows us to cancel. Yes, we love canceling. We can cancel and we can cancel. And that gives us an x on the top over x plus 3. How cool is that? Okay, pause the video here and try this one. I'm assuming that you paused the video. All right, obviously what we need to do first, we can go ahead and multiply these straight across if you want. That will give us 5x plus 3 over 3 times, or I'm sorry, not 3. X times all of this on the bottom. X squared minus 7x plus 7x plus 12. Now I hope you realize that at this point, do not multiply the x through this, because then you're going to wind up with an x cubed, and you're just going to have to turn around and take the x back out in order to factor this, okay? So that's what we need to do next. We have a 5x plus 3 all over x times, well, what multiplied together gives you 12 and added together gives you 7, and looks suspiciously like something in the numerator here. Yeah, how about x plus 3, x plus 4? See, math is really not that hard. It really isn't. All right, rewriting this then, x plus 3, and that's all over x, x plus 3, x plus 4. So I'm going to change pen colors here, and yes, we love canceling. The x plus 3's die a horrible, ugly death and go away. And that leaves us with a single glorious 5 on top with an x times an x plus 4. Now you can multiply that and have that as your answer. It really doesn't make a hoot difference. There you go. Now we're going to bring in our last vocabulary term, and that is dimensional analysis. Write this down in your journals. Dimensional analysis is the process of analyzing units, the units in a problem, to decide which conversion factors to use when you're converting between different units. This is also called unit conversion, okay? So what you're doing here is called unit conversion. How you are doing it is called dimensional analysis. That's how they relate to each other. Okay. So pause the video, write this down. Dimensional analysis. How many minutes are in 1 year? And you're like, oh my goodness. Yeah, right. Okay. Well, how do we start this? Well, we have 1 year. All right. And what we want is however many minutes there are. Well, we need to break this down then. Okay. So we need to convert it. We need to convert it. How many, let's go, weeks? How many weeks are in a year? Well, there's 52 weeks in 1 year. Okay. All right. Well, now, see, here we have year and year. So the years are going to cancel, right? And we're going to be left with 52 weeks. Well, we need to do the same thing with weeks. Well, how can we break down a week? We can do it by days. How many days are in a week? 7. 7 days. So now we've gotten rid of weeks and we're into days. Well, how do we get rid of days? Remember, we're winding our way down to minutes, okay? So, how many days? How many things are in a day? Well, we have 24 hours. Okay, 24 hours in a day. Well, what about an hour? What can we break an hour down into? 60 minutes. And that's our answer, okay? We're now into minutes. You could keep going into seconds, but we don't need seconds. We just need minutes. And that's what we're going to be left with. So I'm going to change pen colors right here. And I'm going to take you back from the beginning. Year can cancel with year here. Weeks can cancel with week. Days can cancel with day. And then hour can cancel with hour. And what are we left with? On the top, we're left over here with a 1, a 52, a 7, a 24, and a 60. So writing these out, we have 1 times 52 times 7 times 24 times 60 minutes. On the bottom, we're left with 1, 1, 1. So 1. That's all there is, 1. So when you multiply all of this out, you get your handy dandy calculator out. 524,160 minutes. Okay. There are 524,160 minutes in a year. That is dimensional analysis, okay? What you did was you converted from minutes to year, or from years to minutes. How did you do it? You did it by dimensional analysis. You figured out, I start with a year. How can I break that down successively until I get to minutes? Did we do it all in one big jump? No. All right, do it a step at a time. We went from years to weeks, weeks to days, days to hours, hours to minutes. Okay? Let's do a real world real world example then. Okay, and it says here, this is example 3, in the 2004 Summer Olympics in Athens, Greece, Justin Gatlin of the United States won the gold medal for the 100-meter sprint. His winning time was 9.85 seconds. What was his speed in kilometers per hour? And your final answer, you need to round to the nearest hundredth. Okay. Well, again, word problem. That means we have to interpret some of what we're talking about here. What we want to end up with is speed in kilometers per hour. Well, what do we have? What do we have to start with? Well, we've got this thing about 9.85 seconds, and we've got 100 meters. Well, what's speed? Speed is distance. Speed is distance per time. Well, the distance we have is 100 meters, and the time we have is 9.85 seconds. So we need to take 100 meters over 9.85 seconds and convert that into kilometers per hour. So let's go ahead and do that. 100 meters over 9.85 seconds. Now you can do this 2 things at a time. We need to go from meters to kilometers, and at the same time go from seconds to hours. So you can do it all at the same time, and that's not a bad way to do it. Or you can do it one step at a time with meters, and then the next steps in from seconds to hours. So we want to end up with kilometers on the top, kilometers per hour. Okay, so we have kilometers. All right, now how many meters are in a kilometer? 1,000 meters. So the meters here and the meters here will cancel, and we're going to be left with kilometers, and that's a good thing. And now we need to convert seconds into hours. Okay, well, let's first convert seconds into minutes. So in order to convert seconds into minutes, seconds are on top, so we have minutes down here. So how many seconds are in 1 minute? There's 60 seconds per 1 minute. All right, well, now we have it in minutes. How do we convert minutes into hours? So when we convert it to hours, so how many minutes are in 1 hour? Well, there are 60 minutes in 1 hour. Okay, so are we done? Well, we're going to be left with minutes cancel minutes, seconds cancel seconds. All right, let's change pen colors while I do this, make it clear. All right, so minutes here cancel minutes, seconds cancel seconds, and we're left with hours on the bottom, and that's what we want over here, hours. Now what about the top? Okay, over here meters cancels meters, and we're left with kilometers on top, which is what we want over here. Okay, so that means now we have 100 times 60 times 60, and kilometers is the only unit that's left on in the numerator. On the bottom we have 9.85 and multiplied by 1,000, and the only unit that's left on the bottom in the numerator is hours. Okay, so all we have to do here now is do math. 100 times 60 times 60 will give us 3,600 kilometers, and 9.85 times 1,000 will give you 98.5 hours. Okay, and they want this then in kilometers per hour. So you take 9.85 and you divide it into 3,600. All right, you're basically reducing this, and what happens, what you end up with here is 36.54, because it says round to the nearest hundredth, kilometers per hour. All right, and that is your answer. Now, if this doesn't make sense the first time through, go back and watch this part, all right? Here you're doing the dimensional analysis, but you're doing it for top and bottom at the same time, or you need to do it for both. We're doing it one at a time, but we're doing it for both, and that's how you end up with this guy right here, okay? So if you don't know how it ends up here, go back and follow how all of this works through this dimensional analysis. That's everything. Thank you for watching the video to this point. If you have any questions, be sure to email me, and I will see you guys soon. Thanks. Bye.